All right. Hi, everyone. Hope you're all doing well. This is going to be fairly low key. I'm just going to go over a few last things from the chapter 12 from the surfaces. And then I'm going to open, and then we'll move on to vectors, and I'll let you guys ask if you have any questions from the video. And then there's a handout. It's like a multi-page handout that's going to take us multiple classes to work through. So I think I'm just going to ask you guys to do the first page today, which is kind of the vector basic stuff. Then we'll move on to the dot product stuff next week. So, all right. So, but yeah, if you have questions or comments or anything, either just throw it in the chat or, let me pull the chat window up so I can see if people chat. Yeah, all right. So we left off class Wednesday. We kind of ran out of time, but I was showing you this, this picture, which was, maybe I can make this bigger, a little bigger. Yeah. So this is the equation of three variables, and I'll write some stuff on this on an iPad in a minute too. So, but this is the function x squared plus y squared minus z squared. And we're setting it equal to different constants. So that may be hard to see, but there's a W, that's a W right there. So when you have x squared plus y squared minus z squared equals -5, you get some kind of like shape like this, which is, it's called a two-sheeted hyperboloid. I'll write that down. As I move ahead, that's -4. I think we saw this movie, if you guys remember, in class Wednesday. -3, -2. So it's getting kind of closer and closer. The two sheets are getting closer and closer. And at 0, we actually get x squared plus y squared minus z squared equals 0, right? Which is the same thing as x squared plus y squared equals z squared, which we've now seen is this double cone shape. So that's kind of cool. The two things come together. The two like different sheets come together in this point right here. And then when I go to +1, so I'm setting W +1 here, then I get this now what's called a one-sheeted hyperboloid, which is kind of cool. It's got like a hole in it. It's like an hourglass type thing or something. And then that sort of changes, as I'm skipping ahead through this. So it's kind of fun to play this movie a little bit and see this thing. Again, it's not fully rendered as it's going, but and I just think it's an interesting idea that, again, like the graph of the function x squared plus y squared minus z squared would be a 4-dimensional graph, something we cannot visualize, but instead we can visualize 3-dimensional level surfaces of the graph, and almost think of the graph or the surface in 4 dimensions or whatever as like a movie of a bunch of 3-dimensional surfaces changing, like morphing, yeah. So I guess, let me see. So let me switch to the iPad here. So it always takes a minute for me to get this. Oops. Yeah. Okay. Yeah. Okay. So you guys can see that hopefully. So yeah. So again, this is functions of 3 variables and their level surfaces. So so the example that we had was the example I'm looking at right now is x squared plus y squared minus z squared. And I'm just a little bit curious if we could sort of see maybe why we get the shapes that we get. I mean, why we were getting those things called two-sheeted hyperboloids and the things called one-sheeted hyperboloids. And how do you know when it's two-sheeted, when it's one-sheeted? So, and I guess I should say this, maybe I'll put a W right here for the 4th variable. So W equals f of x comma y comma z. And so if, we set W equal to different constants, we get different level surfaces, like I mentioned. Right, it's like the 3D version of a contour or a level curve. And for example, when W equals 0, we saw, that's the first one we saw, x squared plus y squared minus z squared equals 0. So that's z squared equals x squared plus y squared. And that's the double cone. But like why when we got, for example, like if we tried W equals -1, I guess the question is, why is this, why did it come up and end up being the picture that we saw? Oops, that's a -1, right? Oops, what did I do here? Minus z squared equals -1. So even within this, so this itself is a surface, right? Like this, now it's almost like forget about the function of 3 variables and just think about this surface. And if you wanted to think about what this looks like, well, you could take cross sections. And in fact, you could take a z equals constant cross section. I'm a little loath to call it a contour because we're not thinking about this as a function. But like, note that if, excuse me. Note that if, so I guess the question is, what does this look like? And you can do some analysis. I guess my point is you can do some analysis like this and try to figure out what something looks like. And I would say that you could sort of argue for yourself that z equals constant cross sections could be nice because you get x squared plus y squared equals a constant, right? So set z equal to constant now. And in fact, for example, we'll set z equals constant, we get, maybe I should say z equals, let me just say z equals c. We get x squared plus y squared equals c squared minus 1. So those are circles, right? So the cross section, if you do the horizontal cross sections, if you cut this surface horizontally, you're getting circles, which hopefully you believe from the picture we saw, right? Like if you notice all those different, the hourglass shapes and the two shapes, the two bubble shapes, those were the cross sections are circles. That's pretty believable, hopefully. But here, notice that if c equals 0, for example, we get x squared plus y squared equals -1. And when you see something like x squared plus y squared equals -1, what do you think? Someone tell me what you think. Or in the chat. Just like a circle. That it's a circle. Sorry, your audio was a little weird, whoever said that. But is it a circle? I guess the question is what points satisfy this? I see maybe someone shaking their head and being like, no, none. Yes, the idea is that no points satisfy this. Like so there are no points. So because x squared plus y squared is always greater than or equal to 0. So so no such points. So that means that there's no cross section when z equals 0. Right. And if you go back to like maybe I'll go back to the picture. Right. So this was just putting in -1. Oh, hello. Oh, -1. It's not what I didn't like. Let me try that again. sorry. Yeah, so there's actually nothing right here at height 0. Right, so you can sort of see that there's like, the cross sections are all circles, like the horizontal cross sections are all circles, right? You can sort of tell that, but there's nothing at 0, and really between -1 and 1, there's nothing. You would need to set the c equal to at least, or the z equal to at least 1 to actually get a cross section. So that's, you can sort of see that's why there's two. That's why there's actually 2 separate pieces to this surface. Does that make sense? I'm hoping that makes some sense. Whereas when you switch to a positive constant, and I'll go back to the notes in a second, but you would actually get, for every z equals constant, you wouldn't have that same problem of having like x squared plus y squared equals negative. And so you'll actually get a nice cross section at each, a nice circular cross section. And you could say, well, there's smaller circles and they get bigger as the z increases. So I mean, I'm just hoping to make this feel like it's maybe plausible, that it's like a plausible picture. So wait, what did I just do? Oops, that's not what I wanted to do at all. In fact, I think I just switched. Hold on, sorry. Just did something so. Okay, so. Give me 1 second. I just messed my audio up unintentionally. Okay, people can hear me talking. Yes. Okay. Thanks. Okay. So here's what I was saying. Like, yeah, over here we got this two-sheeted. There's no such points here, so we get sort of a gap. We get a gap in the surface. For really, if you think about it, for z between -1 and 1. Yeah, up here. I mean, or if I think about here, if I think about setting c, any number less than 1, any number where c squared is less than 1, this will be negative, and you'll get nothing. You'll get no cross section. So that's why we get what's called a two-sheeted hyperboloid. Yeah, you can argue that somehow this is like taking a hyperbola and spinning it around the z-axis or something. Yeah, in fact, maybe I should draw that over here. Like, if I had like, you know, there's. Let me try to draw more nicely. It's not so important, this specific example. I'm just trying to illustrate the kind of thought processes you might want to use. So, right, if you remember what, oh, can I be fancy? Yeah, if you remember what a hyperbola is, it has these slant asymptotes. And if you think of something like this, well, here, I want this to be like z-axis, and this maybe to be like x. So if you think of this is like a hyperbola where it approaches these. And so if you imagine revolving this around the z-axis, do you see that you get that two-sheeted hyperbola? Like, try to imagine like kind of rotating this around, like spinning it around, and you actually get that. That's why, because yeah, this is called a hyperbola. And so when you spin it, it's a hyperboloid. Hyperbola. Okay, but if we did when c is +1, if we set z equals +1, we get x squared plus y squared minus z squared. I'm sorry, w equals +1. Oh, why did I say z? Oh, sorry. So yeah, I set w equal to constant first, then I set z equal to constant. So I want to think about setting w equal to +1 instead. Sorry. Let me just try that again. So if we set w equal to +1, then we get x squared plus y squared minus z squared equals +1. And we could rewrite that as x squared plus y squared equals z squared +1. And now if we set z equals c, we still get circles, but all c values give us, because this is never negative now, as opposed to up here, right? So we always get a nice cross section. And in fact, this is going to be like spinning, like maybe here, maybe I can duplicate this. So I'm going to move this down here, but instead of being this hyperbola, it's now like this hyperbola right here that's being spun around the z-axis. And if you imagine that spinning around, you see how you get the one sheeted hyperboloid. So it's kind of an interesting thing. Like there's two different types of hyperbolas, the one up here and the one down here. And spinning them around the z-axis creates two possibilities, a two-sheeted hyperboloid or a one-sheeted hyperboloid. So I don't know. I guess I'm just thinking about that catalog of surfaces that was in the book on that page that I showed last time and just trying to understand what those are. Okay, so you can kind of do this analysis. If you have a function of three variables, you can sort of try to do this sort of analysis. Any questions about any of that? Okay. Right. So I guess, I don't know if it's worth continuing to draw on here, but I guess what I'm saying is if you spin this around, you end up getting something like that, right? And if you spin this around, so hopefully you can really see those pictures that we came up with. It's sort of interesting. Okay, one final point about these sort of like functions of three variables is we can actually take a surface that we've already looked at. So just like maybe one final point before we move on to vectors. Any surface can be realized as a level surface. Of a function of three variables. This is going to be important when we're doing calculus, like in a week or so, or differential calculus. So what I mean is, say you have, for example, even just something like z equals x squared plus y squared, right? Our standard, that's our paraboloid. That's rotating the parabola around the z-axis, gets our bowl shape, right? We could subtract the z over to the other side. And then we could just call this we could call this thing our f. And then we could say this is the z equals 0 level surface of the function x squared plus y squared minus z. Notice it's not minus z squared, it's just minus z. So you could actually take any, you can kind of go back and forth between, level surfaces and just surfaces. And it's going to be useful sometimes to think of this. I think I maybe mentioned this last class, but it's going to be useful to think of this thing as a level surface of this function instead. And in fact, we can do that for any function, like, there's no, you can always just sort of subtract the z over, right? We can do this. We can do this for any z. I need a different letter now. Let's say g of x comma y, right? We could always rewrite that as g of x comma y minus z equals 0, and then call this, call this f of x, y, z. And so, you might think, well, who cares? But it's going to turn out to be useful in calculus, a useful conceit sometimes in calculus. So we'll do that sometimes. It's kind of random, but okay. Any questions? Always the chat. Okay. So let's move on to vectors. Let me there was a video. I asked you guys to watch this video, right? I was going to pull up the page and then share screen just to ask. Let me share. Okay. Yeah, so I asked you to watch this video, right? I don't think I shared audio with you guys, but I'm just trying to remind you, like sometimes it's it's useful, right? Did you guys have any questions about anything in the video? Did it make sense? Thinking about vectors as sort of these arrows. It's giving me suggestions. Right, you can add them and scale them. There's you can add, you basically add component wise, but there's this geometric way to visualize that. Just pick, we're going to have to think of these arrows as being able to pick them up and move them around. Did anybody have any questions? Anything confusing? You can write everything in terms of the special vectors I and j. I'm really just filibustering here to wait to see if you guys have questions. And trying to remember myself exactly what was in this video. I meant to watch it yesterday before I rewatch it before class. Yeah, magnitude and direction is important. No, we're good. It's notation for the magnitude. And then the idea of a unit vector is going to be important. The idea of scaling a vector down to make it linked one is also going to be important. Because that's kind of like just, if we just want to indicate a direction, it's nice to have a vector of length 1, because then the magnitudes usually represent something like a force or a velocity or, or something like that. But so if we want to express just pure direction, it's not, we'll often scale the vector to be linked 1. Yeah, we're good.
Do you mind actually going over what you were just talking about there one more time, and the stuff after that?
About the
scalar, the scalar vector.
Yeah, okay. So right. So the idea being right that if you have a vector, let's see that I like to listen to lo-fi hip hop in the background when I'm not yeah, so when you have a vector, it always has a length. And the idea is that if you sort of like, if I had a vector of length 5, for example, if I scale it by a factor of 1/5, it's now going to have length 1, right? So maybe I'll just go back to the, let me just go back to the iPad and start writing stuff about, sorry. No, thank you for the question though. It's good. And sorry, let me just pull the iPad back up. Okay. So yes. So vectors. So if we have something like, I mean, my favorite example, and I can't remember if I used it in the video, was something like 3i plus 4j. Right, so that's a vector. So that means you go, so remember I is the x direction, j is the y direction. So that is a vector in the plane. That's like over 3 up 4. So that's that vector right there. So that's our v. And this is the notation, right, that we're going to use a lot for vectors. Although sometimes I get lazy and write just like, sometimes we use, you see like angle brackets. You kind of want to distinguish it from a point. The point 3, 4 is, is right here, as opposed to the vector, which is the arrow from the origin to there. So so the magnitude, the length of this vector is just the standard distance formula, right? It's the square root of 3 squared plus 4 squared, which is root 25, which is 5. And so if you want the unit vector in the same direction, unit just means length 1. Unit vector in the same direction. It's what you do is you just want like, I want a vector, maybe, I want something like this vector right here, if maybe that's length 1 approximately, right? If this whole thing is length 5, then I'm hoping that this length right here will just be 1. And the easiest way to do that is to, the easiest way to do it is just to scale the vector down by a factor of 5, like multiply the vector by 1/5, because that'll make it length 1. So u is 1/5 of v, which here would be 1/5 of 3i plus 4j, which is like 3/5 I plus 4/5 j. And you can check that this is length 1, right? Because the magnitude is, again, the square root of the component squared, just the distance formula. Again, magnitude is just a word for length. And now you get, what, 9/25 plus 16/25? Which is 25/25, which is 1. Does that make sense? I hope that's not an example I exactly did in the video. Is it the same example I did in the video? I'm not sure. It's a bad sign if it's just like, that's the example that pops into my head, and I probably already did it in the video, but I don't think I did this check at the very least. So yeah, so any vector you have, you can always find a unit vector in the same direction, the vector length 1 in the same direction. Again, it might seem kind of random now, but it will be very useful for calculus. Does that answer the question?
Yep, thanks.
Okay, cool. Anything else? So there's this handout on our handouts page on our website. Somehow I hit up. Oh, geez. Okay. Hold on a second. Yeah, I want to show the handout. Lost our website. Sorry. Oh, here it is. Okay. Let me share screen again. It's always so clunky doing this stuff. Okay, so on the handouts page, there's this vectors handout. And so I'd like you guys to pull this up. And like I said, this is a long, like 4-page handout with a lot of different stuff in it. It's going to take us into like a good chunk of next week. But the first page is some pretty straightforward, just you know, just a few problems, vector basic problems. This is a problem from the book I kind of liked, and some stuff here about how do you tell if vectors are parallel. And really just, I think I just want you guys to work on these problems, and we can start from page 2 next week, which is a dot product. And you can read it, section 13.3, if you want to read ahead. Like, I'll post that too. But so I was going to just throw you guys into Zoom rooms and let you just work through these few problems for a little bit, and then maybe come back together at the end and just say like what the takeaways are, if that's cool. I also have a Jamboard. I lost all these web pages that I had. Let me just go to Jamboard. Yeah, I just made a Jamboard for today. So this is what we did. I think we did this once last week, right? When we were online, which was, let me just put this in the chat so you can go to this. Yeah, open this Jamboard up. And so when you end up, I'm just gonna randomly throw you into Zoom rooms again. So, you know, introduce yourself, say hi, work together, and then and I can put a link to this also in the chat, this handout directly in the chat. Oh, that's a long link. Anyways, hopefully that link will work. If not, you can go to the handouts page of our website, and it's there too. Cool. So I'll just throw you guys into Zoom rooms, and then we'll you know, you can work for a little bit, and then we'll call it a day. Sound like a plan? Sounds like a plan to me. Let me always, you know, I'm going to pause the recording because I don't need to record when we're in Zoom rooms. Recording. Okay, so yeah, so it looked like I just tried to jump around quickly. I mean, this was quick, but it looked like people are getting the idea with like 1 and 2. Like we basically did A and B, right? So you do the length, and then you scale down by √5 because the √5 is a length. And then if you want it to be length 3 pointing in the opposite direction, you take your answer to B and multiply by -3, because 3 makes it length 3, and then negative makes it point the opposite direction. The one I wanted to mention, I don't know if every group got to this, but I like this problem just because it really captures the idea of this being, these are displacement vectors, because like the vector A here, it's no X component, no Y component, it's all Z, right? And the Z component is 3. So this is 0i plus 0j plus 3k, or you can just write 3k. But then the important thing to notice is that B and C are also the same vector. They're really just copies of A. Even though their tail is at different points, we think of vectors as displacement. So B is also the vector 3k, C is also the vector 3k. And then you can sort of go from there. I just wanted to make that point before we ran out of time. So yeah. And then, like I said, on Monday, we'll start with page 2. I mean, or maybe I'll say a few things about this parallel stuff also, and maybe I'll make this point again since we're just right out of time. But yeah, so I'll be in the Gather classroom, which remember is linked, I think, below my office hours on the main page. from 10 to 11, and again from, I think I said from 2 to 3 today, if you guys have homework questions. And I'll post the homeworks for next week today also, so you guys can start looking at that. So the homework for Tuesday will be on 12.5, which was the surface stuff, and then the homework for Friday will be starting the like basically 13.1, which is the basic vector stuff. So all right, awesome guys, thanks for coming to class virtually. We'll be back again together next week, so in person. So I will see you all soon.
Thanks, have a good one.
Thank you.
Thank you.
Thank you very much.